Hello, everybody. So today we'll be talking about the sense in which topology may be viewed as a generalization of real analysis, and more generally, uh, a generalization of metric spaces. Okay. So we're going to start with a more philosophical overview about what we're trying to do in mathematics with regards to generalizing things and proving theorems about them. Then I'll take a quick review through what you would have seen in a real analysis course, in particular one where you build up the concepts of differentiation and integration. And then I'll outline more specifically why these things that you'd have seen in that context called open and closed sets are relevant there, because these are what are really important when you start to set up topological spaces. So then we'll do that next and formally introduce what a topological space is and clarify how this generalizes the concept of a metric space from real analysis. Then, rather than just considering individual topological spaces, we'll consider maps between them, in which the notion of continuity will become relevant. And then we'll sort of outline what the broad goal of topology is, which is essentially to classify topological spaces up to some notion of the spaces being the same. Okay. So to start, I wanted to go through some more philosophical points related to what we're trying to do in mathematics. We're trying to do two somewhat disjoint things at the same time. First and foremost, if we have some structure that we're interested in and we're able to prove theorems about it, in mathematics, often what you'll want to do is generalize this class of structures and see what results you're still able to prove. In general, the more assumptions that you put on your object, the better theorems you should expect to be able to prove about it. But then you might want to ask exactly what features about some structure is relevant for proving some given theorems. So if you consider a broader classes of structures than what you were originally thinking about, what exactly can you prove about these? This is going to be relevant for us in our context today because for metric spaces, you can prove really quite a lot. And topological spaces will be generalizations of these. So you want to see what you can still prove, what other assumptions you should put on your topological spaces, right? But then on the flip side, you could ask, why should this be the program of mathematics? Why generalize things? In particular, you should do so if you have specific examples in mind of more general objects than the ones you were originally considering, which you want to understand better, right? So just simply generalizing things arbitrarily is not necessarily interesting, but it should be somewhat grounded in what you have real examples for. Right? So for instance, in the context of topology, a broad class of topological spaces which are not going to be metric spaces are what are called differentiable manifolds. They're not going to be metric spaces, at least without additional structure, right? And these things will be topological spaces. They're going to be examples of these, but they are not examples of metric spaces without this additional structure. Right? So we want to be able to characterize these in some sense, along with many other examples of topological spaces that are actually, this is a very general concept. Okay, so essentially the fundamental notion in real analysis is this concept of a metric. So let's quickly review what this was. So we're going to let our space X be a set. A metric is going to take two elements in this set, send it to a positive real number, could potentially include 0 here actually, and it should satisfy the following axioms. This is very intuitively what you would think of as a distance. So the distance between the same point, like a point in itself, should be 0, right? It should be symmetric, so the distance between x and y should be equal to the distance between y and x. And moreover, it should obey this kind of triangle inequality. So given 3 points, x, y, and z, the distance between any two of them should be less than the sum of the distances between the other two pairs. Okay. So this is very generally encapsulating what you would consider as some kind of a distance. The Euclidean metric would be a nice example of this, but you could certainly consider, I guess, a broader class of examples. Okay. So why was this concept of a metric relevant for real analysis? So what we're really trying to do in the context of real analysis is develop a notion of sequences and series, then talk about differentiation. Well, first talk about continuity, then differentiation and integration, and set up all of these things which you're familiar with from calculus. Right. So I guess fundamentally continuity is playing quite an important role here because you need this to even talk about differentiation in the first place. But I would like to emphasize that continuity itself is already making use of this notion of a metric. Like you have a like delta epsilon notion of continuity in the context of real analysis. These distances delta and epsilon used in this notion are being described with regards to a metric. These are genuine distances in Rn, right? So metric is already appearing here. So you really need this notion to talk about continuity as well as convergence. So for convergence, you have the sequence in the series is going to converge. Let's just say sequence. If for all points like above n, they're like epsilon close to our object. So let's phrase that a little more precisely. So for any epsilon greater than 0, there should exist some n such that for capital N greater than n, in the higher terms in the sequence should be within epsilon of the thing that it's converging to, right? Okay, so distance is playing this notion of a metric is playing a very fundamental role at all levels when you talk about these concepts that you want to understand in real analysis, namely convergence, continuity, differentiation, and integration. Okay, so in the context of real analysis, you use this metric to define notions of open and closed sets, which have their own significance within this context. Right. So an open set in the context of real analysis, remember that we're given a metric here, is one such that for any point, we can construct a ball about that point that is contained in the set. Right. So this ball is defined using the metric. That's the point. Right. And then such a ball could be called like a neighborhood of the point, for instance. A closed set, conversely, is one that contains all of its limit points. So this is intuitively just thinking about R, for instance. An open interval would be open, right? Sensibly, given the name of the thing. And a closed interval would be closed, for example. Right. So in particular, what we would know from this context is that the complement of an open set is closed, and vice versa. Right. But then there's a variety of other properties about open sets and closed sets that we can discern from this definitions. For instance, an arbitrary union of open sets is going to be open, as well as a finite intersection of open sets in this case. Right. Okay. So now I'd like to talk about how we get from analysis to topology. So topology is going to be a generalization of analysis, where in analysis we have this notion of a metric function, and in topology we're going to want to get rid of this. That's really the key point, and we're going to abstract away from this. Right? So we're going to not presume that we have this metric. So what do we want to keep when we go over to topology? So in this case, we want the notion of an open set is going to be the fundamental thing, right? But we're going to start with just some notion of an open set, not defined in terms of a metric, but keep the properties of these open sets that we're familiar with from the context of real analysis, namely these properties which I just said. Right. So formally, let's define what a topological space is. And this is rather considerably more abstract than something you'd see in real analysis because we're not using something so nice as a distance function here anymore in general. So we're going to let x just be some set. Then we'll call the combination of x and tau a topological space. and tau is going to be a collection of subsets of X, and we're going to call this a choice of topology on X. And it needs to satisfy the following axioms, which reflect properties of open sets which we saw in the context of real analysis. Namely, both the empty set and the space itself should be in the topology. This is a collection of subsets of X, right? So these should be in this subset, in this, this collection of subsets. If we have an arbitrary union of sets in the topology, that set should be in the topology. And if we have a finite intersection of sets in the topology, that set should also be in the topology, right? So given these rules, if the collection of subsets of X obeys these three axioms, this is called a topology. So then how does that relate to open sets? Right? These are really the fundamental objects here. The point is that we are now going to define a set to be open if it is a set which is contained in this topology. Right? So note that we did not use a metric to define anything that was appearing here. Right? But it has the properties that we're familiar with from the context of real analysis. Okay. So there were a variety of other concepts in the context of metric spaces which are talked about in real analysis, which would also be introduced via the concept of a distance function, but which we can generalize in a pretty straightforward way to topology. Two ones I particularly have in mind are connectedness and compactness. And the significance of these will sort of appear later in the context of topology, but just remember that, or let's just say, in a general topological space, connectedness, a space will be connected if basically the space can't be realized as the disjoint union of two open sets, for instance. Compactness actually generalizes even more straightforwardly. Every open cover should have a finite subcover. Okay. So all of this was for particular topological spaces, but we can also consider maps between them. And whereas the notion of an open set was sort of the fundamental thing for an individual topological space, in terms of maps between them, continuity is going to be the fundamental concept. And recall that in the context of real analysis, this was defined in sort of an epsilon delta definition, which would have utilized the data of a metric, but we don't have that anymore. So this notion of continuity for a general topological space is just going to be related to how it deals with open sets, right? So in particular, a map between topological spaces is going to be defined to be continuous if the pre-image of any open set in Y is going to be an open set in X, i.e. if we take the pre-image of a set in the topology of Y, it should be a set in the topology of X. Right. So in particular, looking back at that delta epsilon definition from real analysis where we had a metric space, this property would also have been true. If we had an open set in that context, when we pulled it back in this manner from a space Y, it would be open in X. So this is just a direct generalization of a result which we would have proved in terms of delta epsilon continuity for a metric space. Okay, so a stronger notion than just a map being continuous is a map being what's called a homeomorphism. So in this case, this is going to be a bijective map between two topological spaces that is continuous and whose inverse is also continuous. Okay. This is actually relating to a very broad sort of theme in mathematics where you have some notion like this, where you have some kind of a bijective map between spaces. That map has some property, and then its inverse should have the same property. For instance, you could talk about isomorphism of groups or some other algebraic structure like that. It's very similar. But the point is that if we have some map between spaces that functions in this way, this is going to be how we define two spaces to be essentially the same in the context in which we're considering. So for instance, two different topological spaces, if they are homeomorphic, as far as all of the structure is concerned, we would consider these spaces to be the same, right? For all intents and purposes. So in particular, going back to some of these topological properties I was talking about, for instance, connectedness and compactness, if you have two homeomorphic spaces, they better share the same topological properties, i.e., it's impossible to have two topological spaces be homeomorphic if one is compact and one is non-compact, for instance. They have to be exactly the same as far as in the topological sense, which is why I called those things topological properties earlier. Right. Okay, so looking at sort of the overarching goal of topology in this sense then is to classify topological spaces up to this notion of sameness, which we had introduced as a homeomorphism. Right. So this is a very ambitious thing to do in general, right? In any sense, or really for any class of structures. But you might also try to do essentially the converse and try to write down invariants of these topological spaces such that it could show that two given topological spaces are not structurally the same. So they are not homeomorphic. So you could do this via sort of simple things like compactness and non-compactness. If one space is compact, one is non-compact, they're not going to be homeomorphic. But you could also try some more advanced things. For instance, attaching algebraic invariants, for instance, groups or rings to your topological spaces, and then proving some kind of a result such that if two topological spaces are homeomorphic, then their associated algebraic objects are isomorphic. Therefore, if these objects have associated, or if these topological spaces have associated algebraic objects which are not isomorphic, then you can assert that the topological spaces are not homeomorphic. Right? So this is basically the program of algebraic topology, for instance. Okay, that about wraps up what I wanted to say. Hopefully this clarifies the relationship between these two subjects. Topology is one in particular that I really enjoy, so I hope to be making some more videos about this shortly. Okay, bye-bye.